Transferring energy to perform useful work is a common engineering task. This process needs to be done efficiently with as little energy loss as possible. An example of this process is regenerative braking in hybrid cars. Regenerative braking allows us to recover the energy loss associated with slowing a vehicle and store that energy to perform useful work later. It uses the kinetic energy typically lost while braking to recharge the car's battery. This project will use a DC motor and some capacitors to imitate the process of regenerative braking. A DC motor spins a flywheel. During braking, the energy in the flywheel is stored as electrical energy in a bank of capacitors. This energy is then available later to start the flywheel spinning again. First, I'll talk a little bit about regenerative braking systems. Hybrid cars have an electric motor that's powered by a battery. During normal operation, when you're maintaining speed or accelerating, the battery provides power to the motor. The flow of power is in this direction. The battery provides power to the motor through something called the power control unit, or PCU. The motor uses this electrical power to maintain or increase the kinetic energy of the vehicle. When braking, however, we want to reduce the kinetic energy of the vehicle. In a normal braking system, the kinetic energy is dissipated as heat in the brake pads and simply lost. Hybrid cars, however, use this kinetic energy to recharge the batteries in the car. The process is as shown here. Now the motor acts as a generator, which converts kinetic energy to electrical energy. The power control unit uses the electrical energy output by the generator to recharge the battery. Now we've saved some of the energy lost during braking and we can reuse it later. Now let's talk about the project we'll do to emulate regenerative braking. I'll use a DC motor to spin a flywheel. DC motors use the interaction between the magnetic fields created by an electromagnet and one or more fixed magnets to create a torque to rotate a shaft. Spinning the flywheel will store kinetic energy. The faster the wheel spins, the more kinetic energy it has. So the DC motor is converting electrical energy to mechanical energy. DC motors can be used as generators by changing the inputs and outputs. When working as a generator, the motor shaft is rotated and the motor puts out electrical power as voltage and current. So by proper switching, which would be done by the power control unit on a car, the motor can use electrical energy to accelerate the flywheel, or it can create electrical energy by slowing the flywheel down. When we're slowing the flywheel, we'll store the recovered energy in capacitors rather than recharging a battery. Either way, though, this energy is available for us to use later. Next, we'll talk in a little bit more detail about how motors and capacitors work before using them in our system. DC motors rely on the ability of electrical current to create a magnetic field. If you pass electrical current through a wire, you'll create a magnetic field around the wire. The magnetic field can be intensified by coiling the wire around a chunk of iron, as it is on this diagram. If you place the wire near some fixed magnets, the magnetic field from the wire will interact with the field of the magnets to create a force which can turn the motor. So if I put a current through this wire, the force resulting from the interactions of the magnets will cause the shaft to rotate. One final component is called the commutator. It changes the direction of the magnetic field produced around the wire to allow the shaft to keep spinning. Without the commutator, the shaft will just rotate enough to line up the fields and then stop. Now let's do a couple of demos to show how DC motors work and how they can be used to generate electricity. This is a really simple DC motor. I've taped a magnet to my breadboard. I also have a looped wire that I'll run current through from this battery. I'm supporting the wire above the magnet with a couple of paper clips. When I run current through the wire, the magnetic field in the wire will react with the magnetic field from the fixed magnets and the loop of wire will turn. I've made a crude commutator by stripping the insulation off of only two sides of the wire. The system won't start itself up, so I'll apply power and give the wire a little boost. It keeps turning on its own. Now let's talk a little bit about capacitors and energy storage. Capacitors store energy in an electric field. The typical construction of a capacitor is shown here. There are two conductors separated by an electrically insulating material or dielectric, so charges can't get from one plate to the other. Now, if I apply a voltage difference across the plates, I'll accumulate positive charges on one plate and an opposite charge on the other plate. These charges, separated by a distance, create an electric field. If I change the voltage across the capacitor, the electric field changes and I can move charges off of and onto the plates. So in a sense, the capacitor allows me to store charge and recover it later. The amount of energy a capacitor can store for a given voltage is its capacitance. Most capacitors are pretty small. Capacitors in electrical circuits are typically measured in microfarads, which are 10 to the minus 6th farads, to nanofarads, which is 10 to the minus 9th. Now let's look at the capacitors on our regenerative braking system and demonstrate its operation. This is the DC motor I'll use in this project. It's connected to this flywheel. If I apply a voltage to this motor using this power supply, the electrical power will cause the motor to turn, which spins the flywheel. Electrical energy is being converted to kinetic energy. Now let's use the motor as a generator. I've removed the power supply from the motor and replaced it with a digital multimeter to measure the voltage across these terminals. Now, if I spin the flywheel, I'll get a voltage difference across the terminals. The motor can convert electrical energy to kinetic energy or kinetic energy to electrical energy. These are the capacitors on my model system. The system has 10 capacitors, each of which has 2 farads of capacitance. This is a lot of capacitance, so we have the ability to store a large amount of energy. First, I'll use this power supply to bring the flywheel up to speed by connecting the power supply to the motor and turning it on. The power supply delivers a maximum of 18 volts and 3 amps. Since the current's limited, it'll take a while to bring the flywheel up to full speed. The rate at which I can accelerate the wheel is dictated by the amount of current I can deliver to my DC motor. The flywheel's now up to about its maximum speed with the 18-volt supply I have available. Flipping this switch disconnects the power supply from the motor and starts operating the motor as a generator. Now the kinetic energy in the flywheel is being used to turn the generator, and the generator applies a voltage to the capacitors, which store that electrical energy. This is analogous to the process performed by a hybrid car during regenerative braking, when the car's kinetic energy is used to recharge batteries. This meter displays the voltage across the capacitors, which is an indicator of how much energy the capacitors have stored. Notice that the capacitor voltage doesn't get to the 18 volts we originally provided by the power supply. There are always energy losses when transferring energy, which we can never recover. Let's make the flywheel come to a complete stop. Now the capacitors have stored as much energy as they can. I can use the energy stored in the capacitors to restart the flywheel by flipping this switch. Pushing this button allows the motor to run off of the energy stored in the capacitors. The capacitors do allow me to use energy that would normally be lost during braking to start the flywheel up again. This particular system isn't very efficient, so we don't recover a lot of the energy originally available in the flywheel. Still, it's better than losing that energy entirely. This project is mostly about energy storage, transfer, and conversion of energy from one form to another. Devices that convert energy between different forms are called transducers. The transducer in this project was the DC motor. It was used to convert between electrical and mechanical energy. Transducers are an integral part of any electrical engineer's job, since electricity is pretty much useless by itself. Electricity is invariably used to obtain some outcome, such as creating light, heat, turning a wheel, or pumping water. Another important concept in this project is the difference between active and passive circuit elements. Active circuit elements create electrical energy. The power supply we use to start spinning the flywheel is an active circuit element, since it's supplying energy from outside of the circuit. The circuit doesn't know where the energy is coming from. The capacitors we use to store energy are a passive circuit element. Passive elements can store or dissipate electrical energy, but they can't create it. The capacitors also provided energy to turn the flywheel, but unlike the active power supply, the energy in the capacitors was previously stored in them by the circuit.
That was good.
Okay.